Section 3.2, the growth of functions. So what are we trying to accomplish here? Suppose Fn is the time for an algorithm to solve a problem of size n. So the question we're trying to ask ourselves is, what if we increase the size of the input? Right, so the one we'll be focused on here for a second is what happens if n is doubled. So if it takes you 10 seconds to sort 10 items, how long will it take you to sort 20 items? How long does it take you to sort 100 items, right? As you adjust the size of the problem, how does that affect the length of time it takes to solve it? The most straightforward is the linear function here. Assume that the time it takes is n. So the input n takes n time. So if you double the input, it doubles the output. What if the time algorithm is n squared? Well, in this case, if you double your input, you quadruple, right? I take the 2n, I substitute it, I get 4 times the original function. So that quadruples the amount of time it takes it to run. So if you think about it, that's kind of a bad deal. Double the input, quadruple the time to complete it. This gets worse if you look at the cubic. Now it takes 8 times as long for twice the amount of input. And then when you get to the exponential function, 2 to the n, this gets even worse, right? Doubling your input from 2n, multiplying that by 2, means that you do 2 to the n times as much work. Let's go the other way. Let's look at functions that are, quote unquote, for now, smaller. What about log n? This is really spectacular here. Double the amount of input, do one more piece of work. With similar logic, you can show what happens if you double the input on n log n. It's a greater increase than if it were just the function f of n equal n, right? So it's bigger than linear, but it's not that crazy of a jump. And then finally, what about the factorial function? I don't really have a convenient way to note this multiplication, because as you can see, if you double the input, you've multiplied the output by 2n minus 1, all the way down to back down to almost n, right? The one step above it. And so doubling your work when it's a factorial leads to a tremendous amount, just a massive amount of growth in the amount of output here, and the amount of time it's going to take. So we've already seen, hey, if it's f of n equal n, double your input, double the output. What if it's a small adjustment on that? What if instead the complexity algorithm is n plus 2? Sorry, complexity of the function. The complexity of the algorithm is given by the function f of n equal n plus 2. Well, here you double your work. And it takes a little bit of manipulation, but you can write it as 2 times the original function fn minus 2. But now imagine that n is 1,000, 2,000, 10,000, 100,000, a million. That minus 2 doesn't even matter. Like, it's such a small deal. We're going to say it's roughly doubled, right? Brush it off. That's not the important thing. What if your function was 2n? Double the input, doubles the output. So again, doubled. So in some ways, we want to focus on the fact that this is a linear function. We don't want to distinguish between n plus 2, and 2n. The takeaway is that all three of these are linear functions. And so we would say they're exhibiting linear growth. What we do want to distinguish between are these different like base functions, log n log n squared, n cubed. The functions that I had you do on the worksheet after exam 1. So the tool we're going to use is big O notation. This is that complicated definition I had warned about. So if we let f and g be functions, and they're functions that either take in integers and have output in the reals, or they have input reals and output reals, if there exists a c, a multiplicative constant c, and a k that are both reals such that we can put an upper bound on f of x, right? We say the absolute value of f of x is less than or equal to some constant times the g of x for all of the inputs past a certain point, for all x greater than k. What we read this as is we would say f of x is big O g of x. Now, we're going to take a step to make this a little bit easier. In this course, we're only looking at non-negative functions, so we're going to push those absolute values signs aside typically. We're going to start by looking at these problems graphically. Note that I'm going to show you how this extends, how we can do it without the pictures, but first, let's concentrate on the graphs. In red here, I have x squared plus 2, and in blue, I have x squared plus 4. And I'm trying to show that the blue line passes up, is the phrase you'll hear me say, it's how I think of it, passes up x squared plus 2 past a certain point, right? That x squared plus 4 is an upper bound on x squared plus 2. This, looking at the picture, is true for the entire picture we're looking at. In fact, the blue line is always exactly 2 greater than the red line. So I'm going to arbitrarily pick k equals 0, right? Looking at my picture here, it starts at 0. So I'm just going to say, well, I don't know for sure what happens before that. We should know what this looks like. But let's just say I'm going off what's in front of me because that's all I'm asked to do. As long as I'm past 0 and I have one copy of x squared plus 4, I get that this statement holds true. X squared plus 2 is less than 1 times x squared plus 4. This matches the definition, right? The multiplicative constant I've chosen is 1 because I only need 1 times x squared plus 4. When can I start to guarantee this inequality holds? Anything past 0, as long as the input is greater than 0. Let's try this one. I'm going to start to make them more complicated. With this one, the blue line is not always above the red line. But I can see from the picture that it's going to happen. And from the pattern that I see them exhibiting, I believe that once the blue line gets past 1, the blue line is always going to be above the red line. So I'm going to let c equal 1 and k equal 1. And I claim the following statement holds true then, that x squared plus 2 will be less than 2x squared plus 1, as long as you're past 1, as long as the input's greater than 1. Again, matching up from the definition, I only needed a multiplicative constant of 1 times that function to get this to happen. And looking at the picture, I'm saying as long as the input is greater than 1, right? Reading left to right there, I can see that the blue line doesn't pass up the red line until after input 1, as long as x is greater than 1. Let's show that x squared plus 2 is big O x squared. With the graph in front of us, you start to see a problem. And then you look back at the function, you say, oh, how can this be? F of x is literally plus 2x squared. It's always 2 above it. The key here is that we get to pick this multiplicative constant. I just have to prove it exists. So there's any number of answers to this, right? You're picking a pair, a c and a k pair. The one I'm going to go with is I try and draw the line 3x squared. And sure enough, the purple line there gets above the red line. When? At 1. So I'm going to let my c equal 3. and my k equal 1. Then I've claimed that I'm showing that if you take 3 times x squared, as long as you're past 1, as long as your input is greater than 1, that 3x squared will be greater than x squared plus 2. Therefore, I can conclude that it is on the order x squared, or big O x squared, excuse me. Let's look at a more complicated one, and we're going to put it aside the graph. We're going to try and do this without graphing this. Let's show that 2x squared plus 2x plus 1 is big O x squared. And I start off here and I say for x greater than 1, x is less than x squared, and 1 is less than x squared. Where does that come from? How do I know that? Well, these are meant to be statements that are clear or obvious simple facts. You can see here I brought up my picture of the sheet that I had you do after exam 1 to get practice and look at these again, because I just want these to be real obvious. Right, I've drawn x squared, I've drawn x. Let's zoom in there on those two functions and say, when does x squared pass up x? Oh, once I get past 1. Right, that's where all the action is. The blue line passes up the green line past 1, and the blue line will be above 1, also past 1. So I need those to jump off the page. So I get this next statement then. I can say, so 2x squared plus 2x plus 1 is less than or equal to 2x squared plus 2x squared plus x squared. And the first few times you see these sorts of problems done, this can bother you a little bit, but the trick to remember is that I'm dealing with an inequality here. I don't need it to be strictly equal to. So from the first fact there, I have x squared is greater than x, right? Everything that's following here is for x greater than 1. So x squared will be greater than x. So in the first case, I'll leverage that. I know that I can replace x with x squared as long as it's over an inequality, right? X squared will be greater than x. So when I swap those two out, I'm swapping out something greater. I do the same thing with the constant 1. As long as I'm swapping it out with something greater, x squared is greater than the constant 1. So that inequality holds. Do some reduction, you get 5x squared. So if I let c equal 5 and k equal 1, because everything followed from x was greater than 1, I got my 5 from doing that, that manipulation and closing up with that arithmetic. I have shown that it is indeed the case that 2x squared plus 2x plus 1 is less than or equal to 5x squared as long as x is greater than 1. So it is the case that f of x is big O x squared. Let's show that x cubed plus 100x squared plus 1 is big O x cubed. Again, I start with a couple simple statements that come from my sheet that we're just supposed to know, right? Because we know what these basic functions look like. As long as x is greater than 1, x cubed greater than x squared. X cubed also greater than 1. So I do a very similar trick. 100x squared, that will be less than 100x cubed. 1 from my premises up there, that 1, that's less than or equal to x cubed. So as long as x is greater than 1, x cubed plus 100x squared plus 1 is less than or equal to 102x cubed. I found my c and my k. Therefore, f of x is big O x cubed. See an example where this is not the case. Let's show that n cubed is not big O n squared. To do this, we're going to use proof by contradiction. Let's assume that n cubed is, in fact, big O n squared. By definition of it being big O, that means there is the c and the k pair that are real, such that n cubed is less than or equal to cn squared for all the n greater than k. In this case, there's no manipulation. I'm being given this now. I can use that inequality. I'm going to divide both sides by n squared, which is a positive. So I get n less than or equal to c for all n greater than k. All n greater than k, that means n goes off to infinity. So no matter what c you pick, this can't be true. Contradiction. Because of this, right, you saw me do the same technique a couple times, and you'll be thinking, oh, they're all done this way. No, this just works for polynomials. So if I have a polynomial of degree n or less, I can say it's big O x to the n. What about the sum from 1 to n? I'm claiming that the sum from 1 to n is big O n squared. The sum from 1 to n looks like 1 plus 2 plus 3 all the way through n. And I'm claiming that's less than or equal to n plus n plus n plus n times. And that's because for each one of these, they're less than n. 1, that's less than n. 2, that's less than n. 3, that's less than n. That's n copies of n, that's n squared. So if I let c be 1 and k be 1, I have shown that it matches the definition for big O. So the sum from 1 to n is big O n squared. Let's use the same trick to show that n factorial is big O n to the n. N factorial is equal to 1 times 2 times 3 all the way through n. 1 is less than n, 2 is less than n, 3 is less than n, so forth and so on. So now I'll have n multiplied by n times. That's n to the n. Let c be 1, k be 1. I've met the requirements for the definition. I've proved the existence of them. Therefore, n factorial is big O n to the n. Get our first quick corollary here. Log n factorial is big O n log n. Why is that? Well, let's keep one thing in mind. In this course, when we see log n, we assume base 2. So this actually reads as n log base 2 n. From before, from the work I showed just a moment ago, we know that log n factorial is less than log n to the n. My logarithm rules bring that exponent down to the front. So let my c be 1, my k be 1. Therefore, log n factorial is big O n log n. Often what we're interested in is not just a bound. If you go back to those previous problems, there's nothing stopping me from replacing it, with, when I'm doing the one with x cubed, I can replace that with x to the 5th, x to the 100th. I'm often interested in a least bound. We let f and b be as before, that is, they're integers. They go from the integers to the reals or the reals to the reals. We say that f of x is big theta g of x if f is big OG and g is big OF. In this case, we were able to say that f and g are of the same order. So let's show that the sum of I is not just big O n squared, it's on the same order as n squared. We've already shown, right, it was an if and only if statement. We've already shown the one direction. We've already shown that Fn is big O n squared. So what's left to be shown is that n squared is big O Fn. And the proof here is just bear with me. It's gonna you may feel like we're heading from the wrong direction here. 1 all the way through some n from our table. This can be rewritten as n times n plus 1 over 2. This can be rewritten as n squared over 2 plus n over 2. This happens to be greater than or equal to 1/2 n squared. That's just the first term there, right? N squared over 2 is the same as 1/2 n squared. The claim is that as long as n is greater than or equal to 1, I get that sorry, slight typo here. Get my pen. Should be a half. Right, because a half will be less than n over 2, because 1 will be less than or equal to n. And now we're going to get what's going to feel even crazier here. I'm just going to throw that away, right? I don't need that. Certainly, plus a half is bigger than plus 0. So now I have the statement, if you follow the logic all the way through the end, I have that f of n is greater than or equal to a half n squared. Do a little bit of rearranging here. Multiply both sides by 2, and you'll see that n squared is less than 2fn, as long as n is greater than or equal to 1. Well, we've done it. We've got our c and our k. Therefore, n squared is big O fn, so fn, the sum from 1 to n, is on the same order as n squared. Let's show that 2x cubed plus 7x squared times log x is on the same order as x cubed. Now, just looking at this one, you may start to get a feel for what we're going for. We had that table, they were listed in order of sort of growth. And so we're really trying to show that as we increase x, right, if we're looking at 2x cubed plus 7x squared log x, or if we're looking at x cubed, it really is that x cubed that is the determining factor for growth. It's the dominant term as far as growth. It's growing faster. The x cubed is going to grow so fast that the x squared log x doesn't matter. So we're trying to show that to be the case. Again, we start with some simple statements. As long as x is greater than 1, log x less than x. So we start with our f of x. Inequality's missing there. Get my pen again. Sorry for the typos. Right, because I'm replacing log x with x. This is equal to 9x cubed. So let c be 9, k be 1. And we can see that f of x then is big O x cubed. For x greater than 1, log x greater than 0. So one of these, by the way, tends to be a lot easier. it's kind of easy to show that x cubed is going to be smaller than 2x cubed plus 7x squared log x. Still going to complete the argument. X cubed is clearly smaller than double x cubed, as long as we're above 1, as long as we're positive. So 2x cubed then will be, man. So then we add on another thing that is positive, 7x squared log x. Clearly we get something that is even larger, which is my f of x. So let's CB1, KB1. We get that x cubed is big O fx. So they are of the same order. So if you have a polynomial that is degree n, it will be of the order x to the n. If you're asked to show on an exam or quiz a polynomial is a certain order, show that work. Don't just quote this theorem, but otherwise we can just use this theorem.